All right, folks, boy, do we have a fun day today. This is the day where we get to bring it all together, everything we know about a function, and we are going to make the best graphs of our lives. Really, really fun, excited for this. You know, as I watch and I work with my pre-calculus students, my college algebra students, and we work on graphing things like some of them right now are working on graphing rationals, some are working on graphing polynomials, depending on the class that they're in. And you guys did that, and when we did a good job. Okay, but I can't help but think when my classes are working on those, I can't help but thinking like, oh, if they just knew about the first derivative and the second derivative and what that means, man, our graphs would be even better than what they are. And that's what we're going to do today. We're going to start working on putting everything together. And those two topics, rationals and polynomials, is going to be mostly the functions that I'm going to ask you to graph. But now we know a lot more, and this is going to be good. So what are the things that we need to know to make a really good graph? We need to know the domain. Okay. Now, the domain will tie in a little bit with vertical asymptotes or holes. We'll have to kind of interpret what those missing parts of the domain mean. Intercepts, that'd be both x, y, and y intercepts would be helpful. So like I mentioned, vertical asymptotes are holes. Horizontal or slant asymptotes. Think about end behavior. If it's a polynomial, we know if they both go up, down, opposite directions, those type of things. If it's a rational, what we've learned about horizontal and slant asymptotes kind of help us with the end behavior there. Of course, we need to know critical numbers. Okay? We need to know inflection points. Where's the function increasing, decreasing? Where's it concave up? Where's it concave down? Where are the extrema located and what are they? All right. So we're going to just start with a function. I'm just going to do one graph in this video and show you how I put it all together. And you're going to see when the way that I put it together, it almost graphs itself. All right. So here we go. Here's our first function, only function in this video. X cubed over x squared minus 4. So let's start thinking through things here. Domain. Okay. Well, my denominator is x squared minus 4. So I know this is negative infinity to negative 2, exclusive, negative 2 to 2, union, 2 to infinity. What's going on at plus or minus 2? Okay, right, because this is x cubed over x plus 2, x minus 2. Are those vertical asymptotes or are those holes? Those are vertical asymptotes. Remember, the hole would need an x plus 2 or an x minus 2 in the numerator to cancel out with the 1 in the denominator. So I'm going to make a note here that we have vertical asymptotes at x equals 2 and x equals negative 2. So no holes in this graph, just vertical asymptotes. All right, so looking back at my list, we've talked about domains. Might as well grab x and y intercepts while we're at it. X-intercept. Remember, in a rational function, the x-intercept, well, in any function, the x-intercept is the value of x that makes it equal to 0. And where is a fraction equal to 0? Only where its numerator is 0. So x equals 0 is the only x-intercept. Okay. Now, that means it's the point 0, 0. So I usually want the y-intercept too, but what you're going to notice here is if the x-intercept is 0, 0, our y-intercept is also 0. Okay. So nothing really crazy going on there. So domain, intercepts, vertical asymptotes. This is a rational function. If this is a polynomial, we wouldn't talk about horizontal or slant asymptotes, but this is a rational function, so we need to talk about them. And when I look at the degree of the numerator and the degree of the denominator, the numerator is bigger, so there's no horizontal asymptote. But we should notice the degree of the numerator is exactly 1 more than the degree of the denominator. And when that happens, we should recall that gives us a slant asymptote. So we're going to have to recall on what we've learned in pre-calc about slant asymptotes, right? If the degree of the numerator is 1 more than the degree of the denominator, there's a slant asymptote. If this was 2 or 3 more, there wouldn't be. It would just go off to infinity. Okay, but here it's going to be approaching this diagonal line. How do we find that? We find it by actually dividing. And I'm going to need long division by this one because I'm dividing by x squared minus 4. So I have x cubed plus 0x squared plus 0x plus 0 divided by x squared minus 4. So, may have been a while since you've done some polynomial long division, but I look here and I here and I say, okay, x squared times what is x cubed? That would be x. Now I multiply. X times x squared is x cubed. X times negative 4 is negative 4x. I'm going to put that underneath the x's here. And now we subtract. X cubed minus x cubed, gone. 0x squared minus 0x squared, that's gone. 0x minus negative 4x is 4x. Okay. Now notice, okay, I could drop the 0 here, but x squared doesn't go into 4x. So this is actually our remainder. That tells me our function is equal to, what did we get? X I lost it. Where'd my function go? Okay, so when we divided, we got x plus, this is our remainder, 4x over x squared minus 4. Okay, this, when we divide, is equal to that. Now, what happens to this as x goes to infinity? Well, when we look at the remainder part, we look at this fraction at the end, we know this goes to 0. Okay, so as x goes to infinity, this function, this part goes to 0, it approaches y equals x. That's our slant asymptote. All right, so got that. End behavior, this isn't a polynomial. We don't need to talk about that. The slant asymptote is the end behavior because we know it's going to be approaching that line y equals x. All right, so now let's get to critical numbers, inflection points. So our function is x cubed over x squared minus 4. We need to differentiate that. Bottom, d top minus top, d bottom over bottom squared. Let's distribute. And we do have some like terms up there in that numerator. X to the 4th minus 12x squared. Okay, I'm just going to double check my work here for a second. Bottom, d top, minus top, d bottom, over bottom squared. All right, looks good. If we made a little mistake in our quotient rule right now, the whole thing would fall apart. So wanted to make sure that's right. Okay, that is our first derivative. And we know our critical numbers is where our first derivative is equal to 0. Now, a fraction is only equal to 0 only when its numerator is equal to 0. And taking a look at this, I'm going to factor out an x squared. Here we go. So from this, x squared equals 0 gives me x equals 0. X squared minus 12 equals 0. Add 12, take the square root. We get x equals plus or minus the square root of 12. And the square root of 12 is 2 root 3. So we have our critical numbers. Okay. Now we use critical numbers to help split up into intervals of increasing and decreasing. We're going to get to that later. Okay. Let's go to our next thing, which would be inflection points, points of inflection. All right, so here is our first derivative. We need to take a second derivative. Quotient rule again. Bottom, d top, minus top, d bottom, chain rule. Don't forget the derivative of the inside is 2x over bottom squared. So that'd be a 4th. All right, I'm looking at the x squared minus 4s, and there's 1 here. So let's cancel 1 out of everything, like that. I'm going to distribute across the top here. Oh, what is that? 96x minus, now I'm going to distribute, there's a 4x. I'm going to distribute the 4x with the negative. So minus 4x to the 5th, and then plus, is that 48x cubed. So notice 4x to the 5ths are gone. That's awfully nice. How are we doing on x cubes here? Negative 24 and a negative 16 is negative 40, but then we have plus 48, so that's a 8 to the positive. 8x cubed plus 96x over that. Okay, there's our second derivative. Now we need to find the points of inflection by setting this equal to 0. So I'm going to set the numerator equal to 0. I'm going to factor out, I think 8 goes into 96. Certainly does. Yeah, 12 times. So I'm going to factor out an 8x, and then I have x squared, what, plus 12, yep. So I get 8x equals 0, or x squared plus 12 equals 0. So I get x equals 0. Now over here, I would have x squared equals negative 12. I would take the square root, and that's not real, right? That's a non-real solution, actually 2 of them. 2 non-real solutions. And our points of inflection have to be real points. I mean, they have to have real x values. So this is our point of inflection. So we've got critical numbers at 0 and plus or minus 2 root 3. And 0 is a point of inflection, so it's also a critical number and a point inflection, which makes it kind of interesting. We'll get to that. All right, so now we're to the point where we want to put together intervals of increasing and decreasing, and where's it concave up and concave down. Now I'm going to show you how I do this, and I think it takes quite a bit, but I think it's really nice. Like I said, it kind of graphs itself. I'm going to set up a great big number line here, okay, like our x-axis. Okay. So if you recall, when we did intervals of increasing and decreasing, I drew the x-axis and then I split it in intervals to find where is it increasing and decreasing. Okay. And then for concavity, I did the same thing. I drew an x-axis and then where's it concave up, where's it concave down in those intervals. I'm going to mash those two together. All right. Okay. I'm going to put it all together into one, and I'll show you what that looks like. Now I'll actually make a few rows to this. Okay. And the way that I set it up, okay, is that the top row is going to be for f, the second row for f prime, the third row for f double prime, and then down here just could be some notes or little sketches. Okay. Now what I'm going to do is I'm going to write my intervals, and I'm going to use interval notation. Okay. And I'm going to take every important value. So my important values are 0, okay, from the point of inflection, the critical number, so plus or minus 2 root 3, and then the values not in the domain, like vertical asymptotes or holes, in this case plus or minus 2. So I'm going to put them all in and split it up into that many different intervals. All right? So, by the way, plus or minus 2 root 3 as a decimal, 2 root 3 is about 3.46. So that's going to be my first value as I come from the left. I'm going to go negative infinity to negative 2 root 3. That's my first interval. Okay. Now, instead of, like in my diagrams before, I just put a vertical line at x equals negative 2 root 3. I'm actually going to give it its own column. Negative 2 root 3 gets its own column, and here's why. I can put in and find its y value. That's why f gets its own row. I can find exactly where that's a critical number, where that critical number's y value is, which will help me graph. I can also make notes. It was a critical number, so f prime was 0, so I can make that note here and see it when I look, so I can remember what is what. Okay. Now, I'm going to keep going here. I'm going to fill out the whole thing, then we'll come back through. All right? So, our next interval goes from negative 2 root 3 to that next important value, either a critical number, point inflection, or a value not in the domain. And the next value of those is where the vertical asymptote is at negative 2. Okay. Now I'm going to give negative 2 its own column. And I can, here's why this is nice. F, I can cross that off. And f prime and f double prime, because there's no point there. It reminds me that there's not a point here, and I'm going to make a little note, VA, vertical asymptote right there. Then we're going to go from negative 2 to what's our next important value that we had, a critical number, point of inflection, or value not in the domain. It was 0. So 0, like this, negative 2 to 0 is my next interval. I'm going to give 0 its own column. And I'm going to make some notes. F prime was 0 because it was a critical number. F double prime was also 0 because it's a point of inflection. It's both a critical number and a point of inflection. Now let's keep going. 0 to positive 2. Two was a vertical asymptote, so I'm going to just cross those out and write vertical asymptote. Then we're going to go 2 to 2 root 3. I'll put 2 root 3 here. 2 root 3 was a critical number, so that's where f prime was equal to 0. And then we'll wrap up with 2 root 3 to infinity. All right. So we can see really quickly looking at this, negative 2 root 3, 0, and 2 root 3 are critical numbers. 0 is the only point of inflection when I look at the second derivative. So now let's figure out where this function's increasing and decreasing. So I'm going to go to my f prime row, and I need to figure out, is it increasing or decreasing here? So I'm looking in this interval, negative infinity, negative 2 root 3, and I know I need to substitute a value in that interval into f prime to determine if f prime is positive or negative, if it's increasing or decreasing. So I'm going to do that now. I'm going to go, what's the value to the left of negative 2 root 3? Remember, negative 2 root 3 is about negative 3.46, so I'm going to substitute in negative 4. I'm not going to write f prime of negative 4 like before because that just ends up being way too much here. But I'm going to put negative 4 into f prime. Here's f prime. I notice that the denominator is always positive, which is kind of nice. So if I put negative 4 in, I'm going to take negative 4 to the 4th minus 12 times negative 4 squared, and I get positive 64. Yeah, that's a positive. So I'm going to come in my table, and I'm just going to write a plus here. I know that means it's increasing. Now I'm going to continue to substitute into all of these values, all of these intervals into f prime. All right, I'm going to pause the video to do that. You don't need to watch me. If you want to pause and do this as well, just to see what we get, that would be fine. All right, so here's what I have. Increasing, critical number. Decreasing, I think we'd know at negative 2 root 3. It goes from increasing to decreasing. That must be a maximum. I'm going to write a little note here that that's a max. Then I have my vertical asymptote. Now it's negative, decreasing, 0, and then decreasing again. Okay, so this can't be a max or a min. It goes from decreasing to decreasing. And our second derivative is going to help us put that picture a little bit better. put that picture together a little bit better. There we go. And then I've got a vertical asymptote, then I have a negative, so it's decreasing, 0 to positive, increasing. So decreasing, this must be a max. No, this must be a min. It's going from decreasing to increasing. All right, now let's go to the second derivative. Okay. Now I have all these intervals here from negative infinity to negative 2 root 3, and then negative 2 root 3 to negative 2. But remember, negative 2 root 3 is not a point of inflection. And concavity can only change at points of inflection or values not in the domain. So even though it looks like I have two intervals with a point in between, I actually don't need these because it can't change concavity anywhere to the left of that vertical asymptote. Okay. Now, between the vertical asymptote and the point in inflection, it can change, and there, but also over here, it can't change. Okay. The second derivative is never 0, and there's no missing values from the domain, so the second derivative can't change. So I can make this a little bit easier, and I can just put one number into my second derivative for this entire negative infinity to negative 2. And then I'm going to go in here, and then I'm going to go there. So I'm going to pause the video again as I substitute values into my second derivative. Boy, am I glad that on my calculator I can just arrow up and grab my entry before and just change those numbers so I don't have to retype everything in. But here's what I have. In our first interval here, it's negative, which tells me it's concave down. Okay. We have a vertical asymptote. I've got positive, so it's concave up, then 0, then negative, concave down, other side of the vertical asymptote, concave up. Now watch how this is going to put things together. Right here, okay, I know that it's increasing and concave down. What does that have to look like? Increasing concave down looks like this. Then we say we have a max. And then what are we? Decreasing concave down looks like this. It makes sense that we got a max there. We see increasing concave down, reach a maximum, and then we go decreasing concave down. Vertical asymptote. Now in here, it's decreasing concave up. That looks like that. Now here, it was a critical number. The slope is 0, horizontal tangent line, but it's a point of inflection. Look what happens on the right over here. Now it's decreasing and concave down. Looks like this. So what does it look like right here? Well, if you connect these two, you can see that it would look something like this. Here's our point. It's a critical number because the slope is 0, and it's a point of inflection where it changes concavity. This is neither a maximum or a minimum. It's a point of inflection plus a critical number. Okay, and we know what that looks like. Vertical asymptote. Now over here, it's decreasing concave up. On the other side, it's increasing concave up. And we see that we have a min there if we connect them. So you see what I mean by saying that it kind of graphs itself? I know that the graph kind of goes like this. It's got to come up, hit a max, go back down, vertical asymptote. It's got to start up high, it's got to come down, snake its way through, back down, vertical asymptote, start at the top, swing down, hit your min, and come back up. Hey, we're really close to putting this together. Now the only other thing that I would like to put in this are some y values. I want to know, what is the y value of the max? What is the y value of the min? So I'm going to substitute negative 2 root 3. I'm also going to substitute this point of inflection. I want to know what that y value is, and 2 root 3. So I'm going back to f, the original function. Right here, I'm going to put in 2 root 3. Two root 3 cubed divided by parenthesis, 2 root 3 squared minus 4, close the parenthesis. I get about 5.2, and that's good enough for the graph I'm making. That's this one. So it's about 5.2. Now what if I put in negative 2 root 3? I'm just going to insert a negative into my previous entry. There you go. I get negative 5.2. Now how about 0? Well, do you recall that right away we said 0, 0 was one of our points. It's an x-intercept and a y-intercept. Okay. So there we go. That's 0. So now we've got a couple points that we can go through. We've got our vertical asymptotes. Don't forget we have a slant asymptote. Let's put this graph together. Actually, I wanted that to be black. Remember that point was 5.2, so I got to go past that. There we go. So let's put in our vertical asymptotes, which were at plus or minus 2. Remember, you've got this handy. You can look at that vertical asymptotes at plus or minus 2. Okay. Recall that our slant asymptote was y equals x. That looks good, right? Okay. Okay, let's see, what color should I, well, let's graph this thing in red. I'm going to make my pen a little bit bigger. Remember we had 0, 0 as the x and y intercept. Okay. Our max and min, negative 2 root 3, negative 5.2. Now remember negative 2 root 3 is about negative 3.46. So negative 3.46, so right about to negative 3.5, and then negative 5.2, probably about there, just to the right of that vertical line. Okay, and then we had positive 2 root 3, about 3.46, positive 5.2, probably right about there. Now let's look back. What did we say? It has to come up from the bottom, hit our max, and go back down. And now all we're doing is we're putting that in here with our asymptotes. So it's got to approach this asymptote, come up, and then go back down. In the middle, what did it look like in the middle? Starting up high, decreasing, concave up. Hit that point of inflection critical number at the x-intercept that we have, and then flip to concave down, so it's snaking through. So I got to get flat. I can do better than that, I think. Flat, flip. Now, if you want a couple other points there to help you as you're trying to sketch that, that's fine, but I think this is pretty good. Lastly, to the right, where is it? We start up high, we come down, we hit our min, we go back up. Okay, let's put that together with our vertical and slant asymptote, and it looks something like that. All right, got it. Okay, that is a good graph. I like that. Okay, let's type it in Desmos just to check our answers. I want to see that satisfaction of knowing that we did an awesome job. F of x, whoa, getting excited, slow down and type well here, x cubed over x squared minus 4. And that matches beautifully with what we graphed there. Okay, now the scale is a little bit different, size is a little bit different, but we nailed it. Okay, so I think one example is enough for a video right now. I'm at half an hour. This is a big process, right? We just did it with a rational, and rationals get really interesting because they have vertical asymptotes, horizontal asymptotes, or slant asymptotes. There's a lot of different things that can happen. Polynomials tend to be a little bit easier, and you just end up with a lot of max and mins and changing from increasing to decreasing, concave up to concave down. But this is a pretty good one. So thanks for sticking with me. You should feel very accomplished. It's fun to get to this point in what we've learned. I'll see you next time.